warm welcome for today's lecture by Dr. Manjunath Krishnapur, the fourth one in the Pale Blue Dot series. This series of lectures is envisioned to bring amidst us experts in various fields to kindle the inquisitive minds and stoke a dialogue among the larger community in and around Palakkad. We believe it's a responsibility to engage with the society as much as we endeavor to teach students back in our campus. Our director, Professor Sunil Kumar, has been instrumental and very encouraging of this initiative, and we are fortunate for the ample help and support from Sri Ajayan, Secretary, Public District Library. District Public Library. A few words on why we call this lecture series the Pale Blue Dot. We inhabit a small planet, even by the standards of our own solar system, in a remote corner of the Milky Way in an infinite universe. The insignificance of this small pale blue dot in space is probably trumped by our existence and the thirst for scientific and rational inquiry. We only hope to light a spark through these series of talks. So I would request Professor Sunil Kumar to say a few words, and then for Sri Ajayan to also follow.
The speaker of the day, Dr. Manjunath, my colleagues and other people from all walks of life who have come to this lecture series here today. Good afternoon to all of you, and let me welcome all of you to this series. This is the fourth lecture in this Pale Blue Dot series, and we had two of them in person, and then we thought we could continue this online without a break during COVID, and we tried one online, and the success was very limited, so we decided to not have it till the situation comes back to normal, and I think this is what we have now. We are restarting this series. I'm very happy to see that this series is now restarting with the fourth lecture, and also extremely thankful to Dr. Manjunath for agreeing to come here and give this lecture. It's not easy, we know, that to speak on technical topics like statistics, etc., to a public in general. So, I'm sure you'll all be very happy that we came for this lecture today after this talk today. And so I don't want to take more time from you. So I just want to welcome you all again, and then say that, our main problem with this series is two things. One is that we want to have this in the town, and so that everybody can quickly come and participate in that. We are still having some struggle with that, finding an appropriate space and for that. And so if you have any suggestions on that, please come forward. And also we want participation from other people, in the sense not only just coming for the thing, that come joining us in spreading the word, and also letting people know that there is a series like this, and IIT Palakkad and District Library and all very keen on having a conversation between practicing scientists and mathematicians and engineers with the public in general. Okay? And I think this is a very important mission of anybody who is engaged in education today. And I'm requesting all of you to help us in conducting this program successfully with large participation. Thank you and welcome once again. Thank you.
ആദരണീയനായ ഡയറക്ടർ സുനിൽ കുമാർ, ഇന്നത്തെ പ്രധാന അതിഥി ശ്രീ മഞ്ജുനാഥ്, പ്രിയമുള്ളവരെ, സുഹൃത്തുക്കൾ, ഇവിടെ വന്ന് ശ്രീ മഞ്ജുനാഥിൻ്റെ ലെക്ചർ കേൾക്കണം എന്നുള്ളൊരൊറ്റ ഉദ്ദേശത്തോടു കൂടി മാത്രമാണ് ഞാനിവിടെ വന്നത്. പെട്ടെന്ന് ഇവിടെ വിളിച്ച് രണ്ട് വാക്ക് പറയണമെന്നൊക്കെ പറഞ്ഞപ്പോൾ വടിപോയ അഭ്യാസിയെയോ മുടിപോയ സാംസനെയോ ഭരിച്ച ഒരു വികാരമാണ് ഇപ്പോൾ എൻ്റെ മുന്നിലുള്ളത്. നിങ്ങളോട് എന്തു പറയണം എന്ന് അറിയാത്ത ഒരു അവസ്ഥ. അറിവ് അവസാനിക്കാത്ത അത്ഭുതവും ശക്തിയും ചൈതന്യവുമാണ്. അത് നമ്മുടെ ചക്രവാളം പോലെയാണ്. നമ്മൾ അതിനോട് അടുത്തേക്ക് ചെല്ലുമ്പോൾ ആ ചക്രവാളം പിന്നീട് അകന്നകന്നു പോകുന്നത് നമ്മൾ കാണുന്നു. ഈ അറിവിനെ പരിപോഷിപ്പിക്കാനും അതിന് വേണ്ട കാര്യങ്ങൾ ചെയ്യാനും വേണ്ടി IIT പാലക്കാട് നടത്തുന്ന പരിശ്രമങ്ങളെ എൻ്റെ മനസ്സിൻ്റെ നിറവും മണവും ഊഷ്മാവും ഉൾക്കൊണ്ട് എല്ലാ ആശംസകളും നേരുന്നു. ഇതിൻ്റെ ആദ്യത്തെ ചർച്ച നടന്നത് ഡയറക്ടർ സുനിൽ കുമാർ ഒരു പരിപാടിക്ക് വേണ്ടി പാലക്കാട് ജില്ലാ പബ്ലിക് ലൈബ്രറിയിൽ എത്തിയപ്പോഴാണ്. ഞങ്ങൾ അദ്ദേഹത്തോട് അഭ്യർത്ഥിച്ചത് വിപുലമായ സാധ്യതകളുള്ള ഇത്തരം ലെക്ചറുകൾ നടത്താൻ ലൈബ്രറിയുമായി സഹകരിച്ചുകൊണ്ട് IIT തയ്യാറാവണം എന്ന് ഒരു അഭ്യർത്ഥന ഞങ്ങൾ നടത്തുകയുണ്ടായി. ആ അഭ്യർത്ഥന നടത്തിയതിൻ്റെ അടുത്ത ആഴ്ച തന്നെ അങ്ങനെ ഒരു പരിപാടിക്ക് IITക്ക് സമ്മതമാണ് എന്ന് പറഞ്ഞുള്ള ഒരു അറിയിപ്പ് ഞങ്ങൾക്ക് കിട്ടുകയും അങ്ങനെ 2 പരിപാടികൾ നമ്മൾ ഒന്നിച്ച് നടത്തുകയും ചെയ്തു. അപ്പോഴാണ് ഈ സമൂഹം എന്ന സംജ്ഞ തന്നെ ഇല്ലാതാക്കുന്ന വിധത്തിൽ കൊറോണ പ്രത്യക്ഷപ്പെട്ടത്. മനുഷ്യരെല്ലാവരും അവരുടെ വീടുകളിൽ തളച്ചിടപ്പെടുകയും സമൂഹം തകർന്നു പോവുകയും ശിഥിലമായി പോവുകയും ഒക്കെ ചെയ്ത 2 കൊല്ലത്തിന് ശേഷം വീണ്ടും ഇത്തരത്തിലുള്ള ഒരു ലെക്ചർ സീരീസുമായിട്ട് IIT വന്നെത്തിയത് ഏറെ സന്തോഷവും ചരിതാർത്ഥവും നൽകുന്നുണ്ട് എന്ന് ഒരു ഹിപ്പോക്രസിയും കടമെടുക്കാതെ എനിക്ക് നിങ്ങളോട് പറയാൻ വേണ്ടി കഴിയും. ഇതിനൊക്കെ നേതൃത്വം വഹിച്ച ശ്രീ സുനിൽ കുമാർ ഇവിടെ നിന്ന് യാത്രയാവുകയാണ് എന്നുള്ളൊരു ദുഃഖം എന്നെ ഭരിക്കുന്നുണ്ട്. കാരണം ഏത് സ്ഥാപനത്തിൻ്റെയും ഏറ്റവും പ്രധാനപ്പെട്ട കാലമെന്ന് പറയുന്നത് അതിൻ്റെ ബാല്യദശ തന്നെയാണ്. ഒന്നുമില്ലാതിരുന്ന ഒരു സ്ഥലത്തേക്ക് ഒരു സ്ഥാപനവുമായി വന്നുപെടുകയും ഇവിടെ ലഭ്യമായിട്ടുള്ള എല്ലാ കാര്യങ്ങളും തൻ്റെ വരുതിയിലേക്ക് കൊണ്ടുവരികയും സ്ഥാപനത്തിന് സ്വന്തമായ കെട്ടിടവും മറ്റും ഉണ്ടാകുന്നതിന് മുമ്പ് തന്നെ അത് പ്രാവർത്തികമാക്കുകയും അതിൽ അനിതര സാധാരണമായ ചടുലതയും ഊർജ്ജസ്വലതയും കാണിക്കുകയും ചെയ്തു എന്നുള്ളതാണ് ശ്രീ സുനിൽ കുമാറിൻ്റെ പ്രത്യേകത. എത്ര അഭിനന്ദിച്ചാലും അദ്ദേഹത്തിൻ്റെ കർത്തവ്യനിരതയ്ക്കും കർമ്മകുശലതയ്ക്കും ഒരു പകരമാവുകയില്ല എന്ന് പാലക്കാട്ടെ ജനങ്ങൾക്ക് അറിയാം. വലിയൊരു സ്ഥാപനം അത് പടുത്തുയർത്താൻ വേണ്ടി ഒരു ആൽമരം പോലെ അദ്ദേഹം കഴിഞ്ഞ വർഷങ്ങളിലായി ശ്രമിച്ച ആ ശ്രമം നമ്മുടെയൊക്കെ നിരന്തരമായ നന്ദി ആവശ്യപ്പെടുന്നുണ്ട് എന്ന് മാത്രം പറഞ്ഞുകൊണ്ട് അദ്ദേഹത്തിൻ്റെ പുതിയ അസൈൻമെൻറ്റിൽ അദ്ദേഹത്തിന് കൂടുതൽ ശോഭിക്കാൻ കഴിയട്ടെ എന്ന് ആശംസിച്ചുകൊണ്ട് നിങ്ങൾക്ക് എല്ലാവർക്കും നന്ദി രേഖപ്പെടുത്തിക്കൊണ്ട് ഞാൻ അവസാനിപ്പിക്കുന്നു. നിങ്ങൾക്ക് നന്ദി.
Hi, very good afternoon, and I welcome you all for this today's talk. It's my honor and also privilege to introduce today's speaker, Professor Manjunath, who is a mathematician by his own passion and also by own profession. He is an associate professor in the Indian Institute of Science, Bangalore, in the Department of Mathematics. Professor Manjunath has completed his BTech in statistics from the Indian Statistical Institute, Kolkata, with honors, and also masters from the same institute. After that, he moved for his PhD to University of California, Berkeley. Then on, he moved to in the US and Canada. He completed a couple of postdoctoral research, and then he joined Indian Institute of Science, Bangalore in 2009. He is actively involved in the research, which includes mentoring students, then doing the research in his area where he has expertise on, and also teaching. He's a very renowned teacher and very renowned communicator, scientific communicator at the same time. And he has authored quite a lot of highly cited journal papers. And also at the same time, I have to mention here that he has co-authored field medalist Professor Terence Tao in one of the journal papers, which is in the appendix section, which I recently got to know. And also at the same time, he has contributed his research also in the journal of, let's say, a highly cited, highly prestigious journal, Annals of Mathematics. And with this short introduction, we will move on to his talk. And Professor Manjunath, I welcome you all on behalf of all of us. I send you a warm welcome, and we look forward to your talk, sir. Thank you.
So, thank you very much for that very generous introduction, and also for the invitation. It's a great pleasure for me to be here. It's always a very nice thing to see. A new institute which is being built so well. I hope. I want to really give a talk where you get something, so that I get invited again. So sometime. So it's a place I want to come back to. So thank you very much. So to the director, to the math department, everyone for this. As a mathematician, I have. I don't know. When people ask me public lecture, I don't have anything to say to public usually. Okay. So I thought maybe this. Something on statistics is of general interest. So I have prepared some talk. I will tell you a bit more about what I am going to talk about. The point is, by the way, this is meant to be addressed for everyone. So this taking chances, making decisions. So at any time, if people want to ask questions, please interrupt. I usually have in this talk, the nature of the talk is such that I have prepared much more than I will actually give. But it is absolutely not essential what I plan. Okay, so if there are any questions on anything, please interrupt at any time. I'll be very happy to explain a bit more. By the way, is there a pointer? Do you have a pointer? Or? Okay. No. Okay. So it's probably may or may not be needed. Okay. So why? Who needs? So this title may not tell you what it is. Taking chances, making decisions. So many times in life, one has to, there are situations where there is chance involved. You can't be sure if you do something what outcome will come out. So that is where statistics and probability come in. Okay. So, but who needs statistics and probability? Why bother general public with this topic? Well, the point is like this. I'm a mathematician, and some of the others here are mathematicians. So, we hear a lot of good things about mathematics. Mathematics is so important, this, that, etc. But is it really important that everyone should know? What is there in mathematics that everyone should know, really? Is it really important? To be honest, no. Mathematics is important, but everyone does not have to know it. So what does everyone have to know? Well, basic arithmetic everyone has to know. If you go and buy something in a shop, you need to know how to subtract money. So certainly you need to know basic arithmetic. Of course, logical reasoning is important for everything, right? Logical reasoning is absolutely important for everything. So one should have logical reasoning, and mathematics is kind of one of the most purified versions of logical reasoning. So that is very important. The last one, which has become important only in the last maybe 100 years or so, maybe 100, 200, is basic ability to interpret data. Why? You open a newspaper. Every day you are bombarded with numbers. You will be shown polls. You will be election polls, pre-polls, exit polls, opinion polls on various issues, all sorts of statistics. You will be shown how the economy is doing, how it was doing 10 years ago, how it was doing 50 years ago. Has it improved? Has it become worse? Everyone has an opinion on all these matters, not necessarily knowledge of it. Okay, so but having opinions is easy, but it's something that today, if you don't know how to interpret basic data, then you will be somewhat left in difficulty to deal with the modern world. At least it seems that way. So that's why, along with basic arithmetic and logical reasoning, I say that very basic ability to interpret data is essential to people in today's world. And if you are more in a specialized area like engineer or something, then you need to know much more mathematics. But here I am talking about a general educated person, what they should know. Now, what is statistics? Statistics is the subject that aims to extract meaning from data. You see some numbers and you have to extract meaning. And the very important part is to not extract meaning if there is no meaning. Okay, that's we will see examples. And probability is a part of mathematics that provides the conceptual basis for statistics. Okay, okay, this is the general one, but the nature of the talk, you don't have to worry that I'm not going to bore you with some philosophical remarks on mathematics forever. So it is. I just tried to imagine what I was like when, if I was an audience in high school. First thing is my attention span was extremely small. Okay, so I didn't have a long attention span. So this is not going to be one long lecture on one point. So every now and then you will see a white slide with a big something written on it. That means that's a starting point of a new topic. There are many pieces on this top. So if you lose whatever I am saying, if you sleep, if you wake up, whatever, you can jump on in the next topic. Okay, so they are all disjoint pieces. First topic, interpreting numbers. So this is after all the most basic point. You see numbers and you interpret them. Okay, we do it all the time. You see some statistics thrown at you in the newspaper, you immediately have an opinion whether the government is doing well, not doing well, whether the country is going down the drain or up into the heaven, whatever. Okay, so let me ask you some questions. So there will be questions and I would encourage people to answer. Okay, so I'll ask you what these numbers convey. Okay, so the Dean of IIT Palakkad looks at its admission data. Okay, it's all, a lot of data I show here are all fictional. Okay, don't worry. So the Dean looks at data. So he looks at the number of students who applied and number of students who are accepted. So, and he checks by male versus female. So 100 men applied and 57 were admitted. And 90 women applied and 27 of them were accepted. Okay, so what do you make of it? So maybe is there bias against women? No. What? I mean, so when you see such a data in the paper, you soon have opinions about it. So my question is, what is your opinion? Can I say that only 27 women were accepted, whereas 57 men were accepted? Therefore, there is maybe bias against women. Is that a reasonable statement? Anyone? There are also many students I see. So would that be a reasonable thing, that 27 is smaller than 57, so there is bias against women? Would that be a reasonable one? What should we look at? So is it good to look at 27 versus 57? Well, you also have to look at how many applied. If many women didn't apply, what can be done, right? So you have to look at percentage, not just the raw numbers, but the percentage of men who are accepted and percentage of women who are accepted. Now, 57 men out of 100 makes for 57%, and 27 women out of 90 makes for 30%. Okay, so now you have the data. Okay, have you made up your mind? So what does this show? There is maybe significant difference in the admissions for women and men, or maybe there isn't. Okay, how many of you think there is strong evidence there is? Maybe, we can't say whether there is bias or some other reason, but how many of you think there might be this difference is very large? So 30% versus 57%. Would you think there might be something to look into it? Okay, can you raise hands if you think there might be something serious going on here? Okay, I see a few hands up. Okay, so maybe about 10 people are raising their hands. Okay, so of course the dean is worried. 27 percentage points of difference between men and women, looks like a large number. Okay, so he decides to look at department-wise data. This was aggregated data. He looks at the two departments. There are only two departments. So department 1 and department 2, he looks at the disaggregated data. Okay, in department 1, this data comes from these two departments. In department 1, 90 men applied, and in department 2, 10 applied. So total 100, right? This adds up to that. And same for women. 55 women applied to department 1, and what is it? Seven applied. No, what happened? Seven applied to No, something is, oh sorry, where am I looking at? Okay, sorry, 10 applied to department 1 and 80 applied to department 2 among women. And so the admissions is given. If you add up, you see that is correct, right? Okay, something is, yeah, 55 plus 2 is 57, men were accepted. 7 plus 20 is 27, women were accepted. So department wise, one of these must be the offending department, right? Which one is being biased? Well, you calculate the percentage in both of them. In department 1, the percentage of men accepted is 61%, and percentage of women accepted is 70%. Department 2, it is 20 and 25%. Okay? So what do you see about these numbers? Which is the offending department? So you see that in both departments, the percentage of acceptance for women is higher. Whereas overall, there was a huge difference in the other direction, right? So how did this happen? Well, I'm not telling how it happened, but the moral is that when you interpret numbers, it's not trivial to interpret numbers. You may have some conclusion based on those numbers in the beginning, but these numbers show completely different conclusion. The percentage of acceptance is higher for women in both departments. So which one to believe? Whether the aggregated data or the separated data. So it's not clear. Anyway, my main point is that interpreting numbers is not trivial. So when you do it with caution. Okay? So you have to learn how to interpret data, and it cannot be done trivially. In this case, what is happening is, I can tell you that if you see department 2 has lower percentage of, it's a difficult department which rejects mostly people and accepts very few people. If you see for both men and women, the acceptance rate is small. Whereas department 1 is an easier department to get into. It has higher percentage of admission for both men and women, right? 60 and 70 roughly. So what is happening is that for some reason, men are applying to this easier department mostly, whereas women are mostly applying to the more difficult department. So although their acceptance rate is higher in both departments, because department 2 is so strict in admissions, the overall percentage of women is falling. Okay, is this okay? Okay, so that's one example, but main moral is don't interpret numbers too easily. Okay, so another one, case study. Case of unhappy students, which is all students, right? So again, IIT Palakkad brochure for attracting UG students says our classes are very small in size, on average about 25. Okay, all this is fictional, okay? No IIT Palakkad people were harmed in this thought experiment. So I'm just making up some numbers. Okay, so it says to attract undergraduates, it says our classes are really small, you can enjoy. Our class size is only 25 on average. Well, students have already joined, they can't be fooled. So they are saying, oh, no, we are already here, they are lying to you. Average class size is about 35. Don't believe all the propaganda that they are giving in the brochure. So then, whom to believe? Okay. So IIT is saying that only 25 average per class, whereas students are saying on average there are 35 per class. Whom will you believe? Yes? What to do? Okay. So one of them must be lying, right? So who is more likely to lie, students or the institute? Well, let us see. Here is a possible scenario. Okay, so suppose there are only 2 classes. So imagine that there are only 2 classes. One class has 10 students, another class has 40 students. Okay, what the IIT will say is that, okay, on average, there are one class with 10 people, another class with 40 people, average it, you get 25. 40 plus 10, 50 by 2 is 25. So class size is 25 on average. Well, but look at it from the point of view of students. 40 students are in a class of 40. 10 students are in a class of 10. So if you ask the students to write down with their class size and then average it, 40 students will say 40, so 40 into 40. 10 students will say 10, 10 into 10. You average by the number of students, you get 34. So from the student point of view, the average class size is 34. From the IIT point of view, the average class size is 25. So both of them could be correct. Nobody need to be lying. Again, interpreting numbers is not trivial. So just because we think we know the meaning of the word average does not mean we really know. Okay? There are two senses in which average can be computed here. From the institute point of view and from the student point of view. They are completely different numbers. Is okay? By the way, at any time, please ask questions if there are. Okay? Okay. So, done. Anybody sleeping can wake up. Okay? So, mean and standard deviation. This is just a section I want to tell you the most basic points in statistics. Okay? So, what do you learn in statistics? In high school, we were told only about mean and standard deviation. So, let me recall what these are. So, if you have n numbers, if you add them up and divide by n, you get what is called the mean. Standard deviation is a strange beast. It's somebody crazy must have thought of it. You subtract each number, mean from each number, square them, add them up, divide by n, and take square root. That is called the standard deviation of these numbers. What is this standard deviation and why do we care about it? So, standard deviation measures the spread. Okay? So, the idea of interpreting standard deviations is like this. So, this is true for many situations, but not all. Okay, so this is one interpretation of standard deviation. In many, but not all situations, we can say that there are these n numbers, right? There are n numbers. Mean is just if you have to summarize this entire data with one number, you give the mean. If you have to summarize it with two numbers, you give the mean and standard deviation. But how does the standard deviation help you in interpreting the numbers? The idea is that 68% of the numbers are going to lie within one standard deviation of the mean, mu minus sigma to mu plus sigma. 95% will lie within two standard deviations of the mean. And 99% of them will lie between three standard deviations of the mean. So this is true. This is a law of nature. Okay, this is not true universally, but this is a law of nature. It is true in many situations. If you look at heights of people, this is true. If you look at the heights of people in, let's say, Kerala, you find the average, you find the standard deviation, you will find that it is true that 99% of them have heights between three standard deviations of the mean. This is a fact. Okay, I haven't computed, but I know that it is true because this is true. So that is why you get these numbers like 3 sigma, 6 sigma. You may hear these phrases. That comes from this fact that 99% of the numbers lie within three standard deviations of the mean. Okay. So this curve, there is this entire thing comes from a particular mathematical function called the Gaussian function, which is this function e power e minus x square by 2 over square root 2 pi. It's all based on that. Okay, that's the most used and misused curve in all of statistics. So this is true, I said, for heights. It's true for exam scores. If you look at, let's say, 10th standard exam scores in Kerala and you look at the mean and standard deviation, this will be true that 99% of the people will have within three standard deviations of the mean. Okay. Another one closely related to this, the single most important point in all of statistics. If you don't know anything in statistics, if you know this one, then you are in good shape. Okay, you already know something. It's a very related to the previous point, but I'll just make it anyway in a different way. Suppose you toss a fair coin 1,000 times. How many times will it fall heads? Okay, so you toss a coin 1,000 times. How many times is it going to fall heads? Most people will say 500, but it won't be exactly 500, right? It's not going to be exactly 500. It could be a little less, little more. How much less can it be? How much more can it be? Can it be 400? Can it be 300? Can it be 100? It's possible, but is it likely? So how likely is it? We expect that if a coin is fair, half of the tosses will be heads. But how many? So that is what this tells you. This is again a provable theorem if you want, or a law of nature, whatever you want to call it. 99% of the times, if you do this experiment, the number of heads will be within let's say n is 1000, so half n is 500. Okay, half n will be 500. Now what is square root of n? What is square root of 1000? Square root of 1000 is about, let's say, 30. Okay, right? So 30 square is 900. So let's say 30. So it is, if you take 3 by 2 into 30, how much do you get? 45. So if you do this experiment day in, day out, okay, you toss a coin 1000 times, in 99% of the times you will find that you will get between 500 minus 45 to 500 plus 45. That's where the number of heads will lie. So this is the important fact of, this is the most important non-trivial fact in all of statistics. And the fact is the uncertainty will increase. How many heads you get is not going to be close to half of n. The difference will be of the order of square root n. But this is this goes with n, but not as fast as linearly. That's the point of statistics. And depending on context, n could be time, number of samples, various things. So it is used in many things. So lot of things, so many times things develop in time and so accumulate standard deviation. For example, if you look at what happened. Okay. 8 had come off, but now. Okay. Okay, so let me skip this point. Let me just give you an example of where standard deviation may play a role. Okay, so you have two options. You are given two options. Okay, so we will toss a coin. I am going to toss a coin. If it falls head, you will get 200 rupees. If it falls tail, you give me 100 rupees. Okay, this is option 1. Well, the other option is no need to toss a coin. I will give you 25 rupees. Okay, here are two options. Which one do you prefer? That's the question. Okay, so option 1 is we toss a coin. If it falls head, you get 200 rupees. If it falls tail, you have to give me 100 rupees. Other option is no need to toss any coin, I'll just give you 25 rupees. Okay, how many of you prefer option 1? Anybody who prefers option 1? Okay, so there are a few people at the back, I see, some 5-6 people. How many prefer option 2? Okay, I see slightly more number of people preferring. What are the others planning to do? You have only two options, right? So I'm not going to give you any more money than this. So, okay, so you have only two options. So the thing is, the way human psychology works, more people pick the option 2. Now, option 1 has higher average profit. For example, if you do this every day, let's say I give you this option every day. What happens? Half of the days you will win, half of the days you lose. So what happens? Half of the days you get 200 rupees, half of the days you lose 100 rupees. Right? So what happens? On average, how much do you gain? So one day you gain 200 rupees, next day you lose 100 rupees. So you got extra 100 for 2 days. So that means on average, you will gain 50 rupees per day. So if I do this every day of the year, then it's good to take option 1. You get 50 rupees on average every day. Whereas in the second option, you get every day you get 25 rupees. So it seems better that way, but still most people will pick option 2 because there is no uncertainty there. Because the uncertainty is not there, even though the expected profit is higher, you might end up losing 100 rupees, and most people prefer to not do that. So that's where, so the difference is really the standard deviation. In more standard deviation means more uncertainty. Less standard deviation, less uncertainty. And people tend to choose less uncertainty in many situations. So that is the idea. Okay, again, completely different topic. Thanks. Okay, so let's come to sample service. So everyone has heard of sample service, I assume. By the way, any questions about earlier parts? Okay. If not, let's go to sample service. What are sample service? Everyone has seen sample service. So let me just very quickly recall what a sample survey is. So sample survey is this a priori incredible idea that if you want to know something about a population, okay, then it's not a good idea to go and ask everyone. You might think, if I want to know the heights of people in Kerala, if I want to understand what it is like, it's good to go and ask everyone. Okay, or if you want to know which political party will come to power, it's ask everyone to vote, and that's how we conduct elections. But if you really want to know the answer, it's actually much better to ask a few thousand people and you can get an accurate answer. So this seems incredible, a priori it is incredible. Okay, so for example, how is it done? Suppose there are two candidates standing in an election, A and B, and the constituency consists of 100,000 people, 1 lakh people. So one way is to conduct election. That means you ask all 1 lakh people to go and vote, and then you count the votes and you see how many voted for candidate A, how many voted for candidate B, and you will get the result. Another option is you don't go to all the people. You just pick a random sample of 100 people. Okay, 100 seems so small. Okay, there are 1 lakh people in the constituency, but you only ask 100 people. And then you ask how many, but you have to pick that. How you pick them is extremely important, but I will come to that. This is a random sample of 100 people. You can't just say, I will ask all my friends. That is not a good idea. But whatever is this random sample of 100 people, and you ask them if they will vote for A or for B, and if say 40 of them say A, 60 of them say B, you declare that, okay, 60% are going to vote for B, so B will win the elections. This is how poll is conducted, right? This we understand. This is how all polls are conducted. Now, can it be trusted? I mean, is it really something that we can trust, asking 100 people out of 1 lakh? Well, it seems unbelievable, but if you do it, then you will know whether or not it works, and all that it needed to be accepted was to be given a chance. So this happened in 1950s in India, 40s, 50s. Prashant Chandra Mahalanobis, he was one of the important pioneers of statistics in India. So he established the Indian Statistical Institute in particular, and he did a lot of statistics himself. So he introduced sample surveys to India. So here is an example from 1940s of jute survey in West Bengal. Okay, the problem was to forecast how much jute will come out in this year, what production of jute will be there for this year. And you don't know, you will have to, because you can then plan how much to export, how much to use for this, how much to do for that. So if to plan, you have to know what will happen, but you have to see the future. So how do you try to forecast? So there were P.C. Mahalanobis, he advocated sample surveys, but the government said, no, we don't believe all these newfangled things. We will go to every person and ask. So they did what is called complete enumeration. CE means complete enumeration. They went to every jute field, talked to every farmer, tried to figure out how much yield will be there in that farm, and did this all over Bengal, and they did this. Okay, and then they estimated. So what they had to do, there are a lot of jute fields in Bengal, so they had to employ 33,000 people to do this exercise, and spent 82 lakh rupees, which was a very large amount at that time. Okay, and their estimate was what is called 6,304 bales. A bale is supposed to be 400 pounds. So that's the estimate they came up with. What P.C. Mahalanobis did was, he said, okay, you do your exercise, I will do mine, let's see who is better. Okay, so he employed 700 people as opposed to 33,000 people. And then he spent 8 lakhs, 1/10 of the cost that the government had. And he came up with the estimate 7,540 bales. And then next year, when all the cropping is done, then you know what the production is, and the answer turned out to be 7,562 bales. So you can see who got it right? I mean, his estimate is much closer than the government's one. In spite of their spending so much money, so many people, and going to every person, why is it that you got bad results? Okay, more cost we understand, more people we understand, but why is the result worse? After all, they went to every single field and got the result. Why is it worse than what you got from just a sample survey? Well, what happens practically is this. When you have 33,000 people, you can't really train them well. Okay, so you don't know exactly what they are doing there. Okay, they may be not asking the right questions. Some of them may be just filling up their own forms and giving you that I found this and that and so on. So you cannot keep track of all those things. Whereas with a much smaller number of people, you can really train them. And probability works. That's why even with 700 people, he was able to get a very accurate estimate. So that's how sample surveys were introduced. Success of sample surveys led to the creation of many important organizations in India like NSO, CSSO and all that. But conclusions of a poll are only as good as the data collected. Random sampling is the only way to avoid bias. So people get confused all the time. So when election results come, people say, how did this happen? All my friends voted for this party, but how did that party win? Well, your friends are not a random sample, okay? So there is something special about your friends. What is it? Well, they are people like you, okay? So that's why they are your friends. There are a lot of people who are not like you. They are not your friends, okay? So asking your friends is not a good way to gauge the whole population, okay? So there is a question, let me ask you about sample sizes. This is one of the non-trivial points which is very confusing to most people who are not used to statistics. Okay, so let us say a worldwide sample survey poll is conducted to find out people's opinion on some topic. Example, do you believe there is climate change? Okay, some people don't believe for whatever reason, some people believe there is climate change, whatever. So you go to different countries and see what is the opinions of people. Okay, in each country you take a sample. So suppose in Pakistan, this polling agency, let us say Gallup or one of these polling agencies, they went and polled 1,000 people. Means in entire Pakistan, they sampled 1,000 people and asked their opinion. So how many should they survey when they come to India? Okay, so Pakistan, for your reference, has a population of about 20 crores and India has a population about 140 crores. Okay, if 1,000 people, 1,000 seems too less, right? For 20 crores, 1,000 people, it seems small. But okay, I'm not asking you whether that was good. But I'm asking you, if 1,000 people were sampled in Pakistan, how many should be sampled in India? Okay, so anybody with any idea? What would be a good number to sample? So I have given you the total population sizes also for reference. So what would you guess? 7,000. Why? Because it's about 7 times the population. You may say that 7,000 people. That's a very good possibility. Any? Huh? Why 3,000? Square root of 7. Okay, so I earlier introduced the square root law as the most important law of statistics. So maybe it doesn't go up like square root of maybe it doesn't go linearly with the population size. Maybe it goes only square root of the population size. So square root of 7 would be about 3, let's say. So that's another. Any other answers? Anyone else with any opinions on this? Well, the correct answer is 1,000. It's not 7, it's not square root of 7, it is not the square of 7. So it does not matter what the total population size is. Okay, it does not matter. It's actually only 1,000 that is required. This is a point which is very confusing to most people. The accuracy of the estimate does not depend on the population size, it depends on the sample size. If 1,000 people, with 1,000 people, you are able to estimate you are estimating what proportion of people believe in climate change. And you want to estimate it with some accuracy. Let's say to 2 decimal places, you want to know what the percentage of people who do believe in. If 1,000 people suffice in Pakistan, 1,000 suffice in India, 1,000 suffice in China. You do not need any more. The point is the accuracy goes down like, your point is exactly correct. It goes down like 1 over the square root of the sample size, but sample size, not the population size. Population size irrelevant. Okay, so this is very, people are very confused. Do you know how many people are actually sampled when they do polls across India for election polls? People think, okay, India has so many 140 crore people, so must be taking maybe 1 crore or a few 10 lakhs. No, the sample sizes are usually in the order of 5,000, 10,000, something like that. That's all the number of people you ask. Okay. Over. Any questions or comments on this? I started at 4:30. Should I end at 5:30? What is a reasonable time? Huh? Okay. So, okay. So let me go to another topic, completely different one. Tricky situations for getting data. Okay, sample surveys is all about getting data, but how do you get data? Okay, so there are three case studies I have here. So these are all some clever things that most of the times getting data may seem straightforward. You just go to the jute farmer, ask something, ask a question. Of course, it's not as trivial as it sounds. When you do it, you find that you have to design questions well, design the survey well, and all that. But let's say that is doable. But there are some tricky situations where it's very hard to get data. Okay, so one situation, getting sensitive data. There are a lot of sensitive data which people may not want to answer. So like, do you take drugs? Okay, so well, people are afraid. I mean, of course, some people in the population do take drugs, some people don't take. But it's kind of, you can't expect people to answer it honestly. Sometimes people are afraid to answer such questions. So here is a simple question of like that. Let's say we do sample in a survey in some school, and we ask people, we want to know how many people actually copy in exams. Okay. Now, it's a sensitive data for students. If you go and ask a student, did you copy ever in your exams? They will say no, because they don't know what you are up to. They may feel that you are going to target them, right, if you do that. So there are two options, yes and no, but the problem is the question itself is of such a nature that people may not want to answer. So how do you find out answers to such questions? Well, okay, what is the need here? The need is to conduct a poll. I need my answers. So the respondent should answer, but some kind of anonymity should be ensured. Okay? So we are assuming that people are not, they are willing to answer honestly, as long as they are sure that they cannot be targeted. Okay? So if they cannot be targeted, they will answer honestly. This is an assumption, maybe true, maybe not true, but let's make that assumption. So how do you ask questions so that you will get the correct answer? Well, that's the point. The main point is you have to make the poll in such a way that some anonymity for the respondents is kept. So how to go about it? Well, statistician's idea is quite a clever one. I'll show you how it works. So you take some completely harmless question which you really don't care about. Okay? In this case, it is, which ice cream do you like? Vanilla or strawberry? Okay? Which would you prefer of the two? Okay, this is not sensitive data, I assume, right? Nobody is afraid to answer this question. I don't think there is any association of people who get offended on behalf of vanilla or something like that. So people will answer this question honestly. Okay? And in fact, it is by doing a survey, or maybe it has already been done, we know that 60% of the people in the population prefer vanilla, 40% prefer strawberry. Now, how on earth is all this of any help to you in your question of whether people copy in exams or not? What I want to know is what percentage of students copy in exams. What I know is what percentage of people prefer vanilla ice cream over strawberry. Okay? Now, that will be very helpful. Here is how you conduct a survey. Okay? So, this survey works only with intelligent people, probably, because it's a bit complicated looking. Okay? So, how is this survey? So it's like this. So I come to you with the two questions. Both questions are written on this piece of paper. One is question 1, have you copied in some exam? So imagine you are a student, I am the person who is doing a survey. I come to you, I show you this piece of paper with two questions. Question 1 is, have you copied in an exam? Options are yes and no. Question 2 is, do you prefer vanilla ice cream or strawberry ice cream? Again, options are A and B. In both cases, options are A and B. Okay? Options are A and B, let us say. Now, my suggestion to you is, don't tell me what the answer is. You go to a corner, toss a coin. Okay? You toss a coin. If it falls heads, answer question 1. If it falls tails, answer question 2. Okay? So you are just asked to tell me yes or no. But I don't know which question you are answering because you tossed the coin. It may have fallen heads, in which case you are answering question 1. If it falls tails, you are answering question 2. So I don't know, I can't target you. If you say yes, I am not going to say, oh, you copied in exam, because maybe you are answering the second question. So I cannot target you. You are safe. But how is it useful to me? I didn't get the answer. I don't know which question you have answered. Okay? But I don't need to know which question you particularly answered. So imagine there are 200 people, I go to and do this experiment. Okay? Each of them separately tosses a coin and decides to answer question 1 or question 2. Now, by law of large numbers, we know 100 of them will get heads, 100 of them will get tails. So all I know is 90 say A and 110 I have written 1, okay. Sorry. What I meant to say here is A and B. So you asked 200 people, let's say 90 of them have said A and 110 have said B. You don't know who has answered which question. But by law of large numbers, you know out of 200 people, each of them tossing a coin, so 100 of them would have got heads, 100 of them would have got tails. Right? So 100 would have answered question 1, the other 100 would have answered question 2. Well, out of the 100 who have answered question 2, how many will say A? We know that 60% prefer vanilla, so about 60% would have answered A. Okay, so the remaining 30 A out of 90 must come from people who are answering question 1. So this way, even though I don't know what each individual answered, I can know how many people prefer. So 30 out of 100 must have answered A to question 1. So that means 30% of people are copying. So this is the way you collect sensitive data while protecting the individual. Okay, do you agree it's some kind of clever or something? Okay, here is something completely different. Sometimes data is not easy to get. Okay, opinion polls are okay, but how to count the number of fish in a pond? Okay, so let's say there is a lake or pond in your campus and you want to know how many fish are there. How are you going to count it? Okay, well, it's very complicated. How do you count the number of people, first of all? If you want to count how many people are on your campus, will you be able to count? That's difficult, but this is much more difficult. Fish don't tend to cooperate with sample surveys or other things. We are not aware of that. So how do you get this kind of data? Okay, so here is a mathematician's solution. Okay, so this is what might work for people. If it was people, it would be this is how I would go about doing it. Okay, there is a large area in which I want to count people. I kind of divide this large area into small pieces. Okay, maybe equal area, let's say divide into 100 pieces. I just go to maybe 2 or 3 of these sub-regions. I count how many people are there. Let's say in 3 regions I get some number. Then I can scale it up to 100 regions, how many people will be there, right? So this is the way you would count people. But how do you divide a pond into boxes? How do you divide a pond into 100 pieces and count fish? It's not possible. Okay. So here is what a mathematician might come up with. So a solution to a question you didn't ask. That's what we are best at answering. Questions that people ask, we don't know how to answer. Questions that people don't ask, we might answer. Okay, so assume very artificial situation that your pond has 1,000 blue fish. Now, I am not aware of any pond with this property, but this is a mathematician's hypothesis. Suppose I know there are 1,000 blue fish in your pond. Then, this is what I am going to do. You catch 200 fish. So you just catch fish, like fish in different regions of the pond, just catch fish. Let's say you catch 200 fish. Okay, you may fix it up or whatever. Let's say you catch 200 fish, and suppose out of that there are 25 blue fish. Now, can you guess how many fish are there in the pond? Okay, so out of 200 fish you catch, there are 25 blue fish. So, how many total number of fish should be there in the pond? What is your guess? Anybody? Yes? Yeah, any volunteer for an answer? So, out of 200, 25 are. So that means, what is the percentage of blue fish? 1 out of 8, right? 25 of 200 is 1 out of 8. In other words, this is 8 times the number of blue fish. So assuming the same proportion works for the pond, the total number of fish must be 8 times the number of blue fish. Because in the sample, the total number of fish is 8 times the number of blue fish. Even in the population, maybe the total number of fish is 8 times the number of blue fish. So that would give you the answer 8,000. Right? 200 by 25 into 1,000 will give you 8,000. Well, excellent. You have answered a question which was not asked. If the pond has 1,000 blue fish, you can find. So, but that's not your pond. So what do you do? Well, the statistician's answer is the following. Well, catch 1,000 fish, color them blue, put them back in the pond. Right? Now you have a pond with 1,000 blue fish. Now you can repeat the experiment. Right? So this is how you solve this problem. This is called a method of capture and recapture. When you count animals in the forest, various things, this method can be used. Now, blue doesn't mean blue, you tag it in some way. That's all I mean. Okay, so this is the way you, problem that looked, what looked like an artificial problem that we were solving is not artificial. It can be created. You can create that situation and solve it. Okay. So there is one more. This has come to fore in recent times because of the pandemic. Many of you may know this. Nevertheless, sometimes there are expensive medical tests. So let's imagine there is a not very common disease, and blood test has to be conducted to find out if somebody has the disease or not. Let's say there are a lot of people, you want to find out who has the disease, who doesn't have the disease. But the test is quite expensive, so the government doesn't know whether to do the test or not to do the test, because it's very expensive and it's a rare disease. Most of the results will come out negative, right? So it's a waste, it's all a waste of money, right? So to test or not to test, that's the question. Okay. So what should you do? Okay. Here is a statistician's idea, very clever idea, which many of you may know. So, since the test is expensive, the statistician says, okay, do the following, gather 10 people, okay, collect blood samples from each of them, pool it together, just combine all their blood together, okay, and then test it. This combined sample, it is not the blood of one person, but of 10 people pooled together. Now, if none of them has disease, let's say the test is 100% accurate for simplicity. So if none of them has disease, the test will show negative. So you can say, you can clear all 10 people out in one shot, right? One test for 10 people done. But what if one of them has, even if one of them is diseased, the test may come out negative, in which case, you know that out of these 10 people, there is one person, at least one, maybe two, maybe three, who have the disease. So what do? Well, then you separately test each of the 10. Okay, so in the first case, if it comes out negative, everyone cleared together because nobody has the disease. In the second case, you have to test. So in first case you saved because you did one test instead of doing 10 tests. In the second case, you wasted. Instead of doing 10 tests, you are ending up doing 11. Right? Because you did the first test, came out positive, then you had to test each of them separately. So you did 1 plus 10, 11 tests. So, but does this save for you? Yes, because the disease is not very common, it saves a lot of money. Because imagine there are a total of 1,000 people whom you are testing. You group them into groups of 10. And let's say there are only 2 people who have disease, which is reasonably high for a rare disease. But let's say out of 1,000 people, there are 2 people who have disease. Okay, so now I am grouping these 1,000 into 100 groups of 10 each. Okay, so there are 100 groups of 10 people each. What happens? These 2 people are in some 2 groups. Those 2 groups will take 11 tests each because one person, that group, you do the first test positive, so you have to do again. So 11 tests. Second group, you have to do that. But all the other 98 groups are cleared with just 1 test. So how many tests did you conduct in total? 98 into 1 plus 11 into 2, which is 120. Whereas there are 1,000 people. If you were doing naive testing, you would have tested 1,000 times. Now you saved the cost of 880 tests, right? So this is called the idea of group testing. This is an old one. It is of considerable importance theoretically and in statistics. It is actually used. Of course, there is a caveat. You cannot mix too many blood samples. The accuracy of the test goes down. But nevertheless, this is a useful idea. Statistics in the mind, okay? Okay, so, well, whatever. Don't bother about what is here. So there is some person, okay, completely new, okay? If you lost me completely in previous things, you can listen again, try once more. So there is some person X who is either a doctor or a mathematician, okay? So I have told you this, you don't have to consider any other possibility. The person is either a doctor or a mathematician. I'm going to tell you some things about the person, then you have to guess whether it's a doctor or a mathematician, okay? So X is intelligent, very systematic, introverted, doesn't like talking to people, very absent-minded, okay? So these are the characteristics of this person X. And I have already told you, it's either a doctor or a mathematician. You don't have to consider any other possibility, okay? So you have to guess, is it a doctor or is it a mathematician, okay? So what is your guess? Mathematician? How many of you say mathematician? Okay, I see many hands. I don't have to count, at least 20, 25 people. How many of you say doctor? One? Only one? Two? Huh? Can be a bad doctor. Okay, that's possible. So you think all mathematicians are bad? Okay. Okay, so very few take us for doctor. So somebody else said doctor. Why? You think doctors are more like that? Okay. Well, I'm very happy to hear that. I am personally very happy to hear like that. See, the stereotype of a mathematician, the stereotype of a mathematician is these things, right? So they tend to be absent-minded, they tend to be this and so on. Let's admit all that. It's possible. Okay? So the answer is still more likely to be a doctor. Okay, I'll explain why. So let's admit the following. Let's admit all the stereotypes about mathematicians. Mathematicians tend to be more introverted. Maybe. I don't know, but let's accept that. Mathematicians tend to be absent-minded. Let's accept that. It's probably true anyway. So maybe intelligent. Let's say mathematicians are 10 times more likely to have all these properties than doctors. That's possible, right? It's not that doctors will never be this. Maybe mathematicians are 10 times more likely to have this property. But how many doctors are there compared to mathematicians? 100 times more, at least. So what is this person more likely to be? There are way more doctors in the world than mathematicians. Because there are many, many more doctors applied. Okay? So let me show it to you in a picture. This picture will explain this. So on the left side, so there is a picture. The left side of the square are all the doctors, right side of the square, all the dots are mathematicians. And that is really in proportion to the real life situation. I mean, there are so many doctors compared to mathematicians. Okay? This is true. Now what is blue? Blue means they don't have, they don't have all these properties. Okay? Blue means they don't have these characteristics. Red means they do have these characteristics, okay? So here are all the doctors. Some of them tend to have this very small fraction. Maybe 1% of doctors tend to have these properties. Or maybe 10% of doctors have to these qualities. They are marked in red. Here one, here. You see a few doctors have these qualities. Well, others don't have those qualities. Whereas here among mathematicians, much higher incidence, or most of them tend to have these qualities. Only one here, very nice, good mathematician, he is up there, okay, doesn't have these qualities, okay. So now, that's correct. But still, if you see how many red points are there on the left and how many red points are there on the right. There are more red points on the left than on the right. Even though there are more, mathematicians are more likely to have these properties, since there are so many more doctors, the number of doctors who are absent-minded is way more than the number of mathematicians. For example, if there are 100 times more doctors, and only doctors are 10 times less likely to have these qualities, still there will be 10 times more doctors who are absent-minded than mathematicians. Okay? So this is a very famous, that's why I wrote most common statistical fallacy. This is, in technical terms, it is confusing probability of A given B with probability B given A. I don't want to explain what that is. Okay, so here is another one about statistics and the mind. Psychology of probability. This is a famous, so you may have read the book of Kahneman, Daniel Kahneman. These are economists. They studied lot of things. So Kahneman has a book called Thinking Fast, Thinking Slow. It's all about sort of some kind of psychological aspects of probability and rational decision making versus irrational decision making, that sort of thing. Anyway, there they give an example of this type of experiment where they say they give this information to a person and then they ask. Linda is a 31 years old single, outspoken, very bright, majored in philosophy. As a student, she was deeply concerned with the issues of discrimination and social justice and participated in anti-nuclear demonstrations. Choose the most likely option. Linda is a bank teller. Second option is Linda is a bank teller and active in the feminist movement. Okay? So you have two options. How many of you pick option 1? You have to choose the more likely option. Okay? So I see 3 people, 4, 5 people picking option 1, 5, 6. How many of you pick option 2? Linda is a bank teller and activist in the feminist movement. I see a few more, not many more. Okay, so maybe 7, 8 people. Oh, okay, I see a few more there. Okay. So the fact is, many times people choose the second option. But second option in this particular case should never be chosen. Why? I said choose the more likely option. Now, the set of bank tellers who are active in the feminist movement is a subset of all bank tellers. How can this be more likely than that? Right? These people are all part of this also. Okay? So what we really interpret when we think of this question, I don't know what is the real moral of this question actually. They did this experiment, they found that in many experiments, people do choose option 2, as did many people here. So what is it? We don't know. Overall, maybe human mind is not naturally trained to gauge probabilities. We have to train ourselves to gauge probabilities. Here is a different one. Okay? Okay. So here is a question I will ask you. So do you often find that the bus you are waiting for is the last bus that comes? Everyone else gets their bus and you are the one who is stuck in the bus stop. Or you are in the supermarket or waiting for some train ticket. Nowadays, no, people don't go and wait in queues, but when you wait in a queue, your queue is slowest, longest. The others are all moving fast and you are the one who is stuck. Or you are caught in traffic jam. The other side traffic is moving very nicely. But you are caught in this side. You wish, why was I not on the other side? Does this happen to you? Has this happened to any of you? Yes? You feel? Why does it happen to you? I mean, why is the world so unfair to you? Right? The world seems to be conspiring against you, making you wait in long queues, putting you in traffic jams. Why? Are you a very unlucky person? Well, the answer is because you are a typical person. Okay? What do I mean by that? What is the difference between a long queue and a short queue? Fundamental difference. Okay, that's the main difference. A long queue, by definition, is a queue with more people. Short queue is a queue with less people. So where are you more likely to be, among more people or among less people? You are more likely to be among more people. What is a traffic jam? It is a place where a lot of people are stuck. What is the place where people are moving fast? There are very few people there. So where are you more, if you are a typical person, where are you more likely to be? Where there are more people. So this is just because you are a typical person. Okay? So there is no other, okay, there may also be a psychological angle to it. Sometimes people tell me that you tend to remember negative experiences more than positive ones. That may be there, but first you should realize that there is a basic statistical reason why this is what is to be expected. You are like, okay, you may be very special to your mother, but you are a typical person in other ways. Okay, in all other ways you are a typical person. Let me ask another thing, which we get told, at least in my family. So, do people in your family, older generation, tell you how people were so healthy, so this, etc., but this generation is all really messed up? Okay, you get all diseases. My grandmother was so good, she could drink 1 pot of ghee every day and fall on a rock without anything happening to her, etc. You hear this? Have you heard this kind of stuff? But is it really believable? I mean, we should be better today, right, than earlier times. Is it really true your grandmother's generation was better? But let's assume they are not lying. They may be true. They may be saying the truth, that your grandmother was this healthy, they were that healthy and all that. So, if this is true, why is it true? Huh? Well, any options? Anybody who wants to volunteer an answer? Why is it? Why does it? Yes? Okay, so because your grandmother is an atypical person of her generation. In what way? She is a grandmother, okay? So this means, by definition, she actually somebody who lived long enough and was healthy to produce children who produced children. So that itself completely separates her from people of her generation. Sometimes you can ask, when people tell you this, if you ask, you will know that maybe that grandmother had a sister who died when 2 years old or something like that. So it does happen. If you probe, you will sometimes find out. So your grandmother is not a good sample of the population of that time. Okay, if you want to, so this is related to whether, just like your friends are not a good sample of the larger population, your grandmother, if we take all our grandmothers and take some data about them, that will not give us a good sample of, let's say, 1950s or something like that. That's not a good sample, because grandmothers are not typical people of that generation, they are atypical. I can do a direct survey now, okay? So please raise your, let's assume our grandmothers were a good sample of the 1950s generation. Let's assume that is the case. Okay, so then we should be able to use data from that to deduce something about the 1950s generation. Okay, so please raise your hand if your grandmother died before the age of 10. Okay, anybody? Huh? I see one. Okay, surely. So, if you have a grandmother who died before the age of 10, please raise your hand. Okay? Okay, nobody. So, based on this sample, we have to conclude nobody died before the age of 10 in 1950s. Right? If this was a good sample for that generation, your conclusion would be nobody used to die before the age of 10. It cannot be really true. It's ludicrous. The reason is grandmothers are not a good sample. They are very special in that they are grandmothers. Okay, so that's the point. So this is called sampling curve selection bias. So a very similar problem is there. This is a problem, this is a historical one of fixing airplanes in World War II. So in World War II time, this is from the United Kingdom, from there. So see, war is a time of shortage. You can't do everything. Okay, so what happens is they have a lot of planes and they get damaged, they have to fix them. If somebody comes and says, see, the cushion is torn, they will just kick them out. No, this is not the time when you can complain about a torn cushion or something. We can only fix really important stuff. This is a time of shortage, okay? So you have to see what are the things, which ones to fix, which defects to not fix. So they did a survey, engineers looked at the planes and they looked at how many of them were shot in various different parts of the plane. Okay, so among the planes, so this is some bullet holes per square feet. Okay, so they looked at these fighter planes which had bullet holes, and they found that there were about 1.11 bullet holes per square foot in the engine area. In the fuel system area, which is another part of the plane, there is maybe 1.55. So higher, more planes have been hit in this one. And if fuselage is the body of the plane, even more there. And there are other parts, 1.8. So the engineer said, okay, so more planes are getting hit in these parts, so fix these first. give priority to fuselage and only then to fuel system and then to engine. Okay? Sounds sensible because more things are getting hit there. So they showed it to a statistician, a very famous statistician, Abraham Wald, who incidentally died in Kerala somewhere actually, in an air crash. Okay, but that has nothing to do with airplanes. He suggested everything is good, just reverse the priorities. First fix the engine, then fix the fuel system, then fix the fuselage. Why did he say that? Very good. So a statistician has always to be alert to the point that the data you see has been pre-selected for you by nature. There are certain types you don't see. You don't see the planes which don't come back. Why are so few planes with bullet holes in the engine part? Because maybe that's so fatal they don't come back. Maybe all parts are hit, but if damage to engine is so fatal they don't come back. Damage to fuel system is slightly less fatal, so they come back a bit more, but not necessarily. So in that sense, the more vital thing to fix would be the engine rather than the fuel system or the fuselage and so on. Is okay? Okay, so maybe this is 5:35, so shall I stop here? Okay. Okay, so there are, as I said, I have many more of these topics, but I hope you at least like some of them. And okay, thank you for your attention.
From where your all examples are getting?
Oh, these examples. Okay, so this, I mean.
Any books or any resources?
Yeah,
I want
definitely.
to know.
Yeah, of course, except those that I made up. Like the beginning parts, those are real, by the way. Real in the sense, the beginning things when I showed you this business of this data, this was made up data, but it actually happens in real life. So in fact, there was a study in Berkeley with the dean of who's looked at two things. So this one is called Simpson's paradox. It's a famous one in statistics. And some of these are made up, some of these are real data. Well, where did I get them? You know, I studied statistics for 5 years. Okay, so so I have some things from various places. I collected them and with them. I don't know. There is, if you want books, if you want to read books on this kind, there is a not available book actually. I don't know. At least if you find it somewhere, one can be bought for your library. Like there's by C.R. Rao called Statistics and Truth. It's kind of fun to read. Okay, Statistics and Truth by C.R. Rao, one of the most famous statisticians of India. So there are some others which are there in other mathematics books. So when mathematicians want to explain mathematics to general public, usually you have to come to statistics or some other things actually, because that's what is matter. So for example, this example I gave, well, this one is a very famous, this is also from Kahneman and Tversky, for example. They write it like this, they call it represent, but this is a very well-known thing. In probability textbooks, it's given as Bayes paradox. There is a very different situation in which, for example, this occurs. Somebody goes to get tested for cancer and they test positive for cancer. But it turns out that it was false detection. It's exactly like this. Okay, so most of the times, those who test for cancer tends to be false detections rather than, even if the test is very accurate. So this is called Bayes paradox, and but this one, there is it's there in many places. So there is one fun book by I think Jordan Ellenberg called How Not to Be Wrong. It's a popular mathematics book, How Not to Be Wrong. I think it is given there also, this particular one. Okay, I don't know one place where you can get all of this.
It's fine, sir. Thank you.
How to gamble if you don't listen to your mother and still want to. Okay, so this is a single slide. How to put money? That was the question. If you invest, so if you want, shall I tell this? Is it okay? Yeah. So this is just a single slide. This is another non-trivial see, lot of things, you may do lot of statistics and then say something which is anyway what a person would do. But here there is a non-trivial point. Okay, so it's a question of how to invest money. Okay, don't take these things, recipes exactly literally. There are many caveats in all these things, but this is the rule. Suppose you invest money M on it, there is a bet. You can place bet on it. If you put M rupees on it, then two possibilities. You win the bet, then they will pay you extra M rupees. If you lose the bet, you have to give away your M rupees. Okay, so that is the rule of the game. Now, let us say there is a probability P of winning the bet. P could be 0.6, 0.4, 0.5, something. Okay, so you are going to, if you put 100 rupees as the bet and you lose, you will have give away 100 rupees. If you put and win, you will get extra 100 rupees. So you will have 200 rupees in the end. So question is, suppose if you have a total of W rupees, W is let's say 1000, and let's say P is 0.6. So how much money, how much of it should you bet? Okay. So first point is, if P is less than 0.5, don't bet anything, keep your money safely. Okay, don't bet anything. If P is more than 0.5, you tend to make profit, right? I mean, that is clear, right? You tend to make profit. But is it a good idea to put all your money on this? Turns out it's a non-trivial fact that no, just because it's profitable doesn't mean you put all your money on it right away. Okay? You should do it in such a way that your long term, if you keep doing this, you should make money, as much money as possible. Then there is something called Kelly's criterion which tells you how much you should bet is 2p minus 1. If p is 0.6, 2p minus 1 will be 1.2 minus 1, 0.2. That means you bet only 20% of your total wealth on this. You keep the rest. You may lose, gain, but then you have some amount of money. Again, if you get the chance to bet again 20% of it on this and go on. That is what will maximize your long-term growth profit. Okay? So anyway, if it's a casino in which you go and play, P is always less than 0.5, so just keep your money. Okay? Don't even think that the casino is not running to make money for you. It is being run to make money for the casino. It's very clear P is less than 0.5. On the other hand, when is P more than 0.5? Maybe stock market, because there is an actual wealth creation. If there is actual wealth, of course, lot of stock market is random speculation. I can't say it is true, but there is actual wealth being created, so there is possibility of actual wealth creation. So then maybe you can make profit, but of course you will never know. So nobody will ever tell you P. So this is a somewhat theoretical point. If you knew P, this is how much you would bet, but you will never know P. So what should you do? I have no recipe for you. Yeah. So that is that was the.
Professor, in the example that you gave of 57% of the boys versus 30% of the girls being admitted to the institute, is there any probability where that actually does show that boys have a roughly double the chance of being admitted as?
So it is, now what to interpret it as? It's a tricky point. I mean, it is true that there is a considerable difference, but you have to find the source of the difference. So in this case, it turns out because for some reason, less women are applying to Department 1, where its acceptance rates are higher, and more are applying to Department 2, and for men it's going the other way. Now, this is, as I said, a made-up example, but you have to then look into why that is happening. Okay? Is there a reason? If at all you want to address this issue, if you feel there is something wrong with this, you have to inquire into why women are not applying to Department 1, why men are not applying to Department 2, and look into it. It's like that. So my point is that based on this, it's hard to give the conclusion. Sometimes we should not conclude. If it's not possible to conclude, we should not conclude. That's a very important lesson in life, right? So just because there is a question doesn't mean there has to be an answer. Okay? So for example, suppose I tell you that in a country, okay, let's say, not say which country, there are only 45% women and 55% men. Okay, maybe you will recognize a country like that, but okay, let us say. So what should you do about it? If I ask you that question, what would you say? There is a country in which there are only 45% women and 55% men. So, anybody, any answer is okay. There is no. Would you have any opinion on it?
Yes, it's a skewed sex ratio.
There is clearly a skewed sex ratio. What should be done about it? Well, my point is, based on this, we cannot say. There can be two completely different reasons why this can be happening. Okay, so I am saying that based on this, there is a skewed sex ratio is clear, but why it is skewed is not clear, and your course of action, just because you feel strongly about it, the course of action you take may not be the correct one. For example, you may say, oh, there is some infanticide of women, that is why that is happening. That's one possibility. There is a completely different possibility. Okay, so imagine all women die at the age of 60, all men die at the age of 70. Okay, maybe there is no infanticide at all, but for some reason women die at the age of 60, men die at the age of 70. Now, if you look at the current population, how many women will be there? All the women who were born in the last 60 years. How many men will be there? All the men who were born in the last 70 years. Obviously, it's more. Okay, so there can be, so in the second case, you should worry why, what is happening at this older age, why women are dying at 60. I mean, this is just a hypothetical example I am saying. So, in one case, the reason could be at infant stage, and the other case, the reason could be why, what is happening at old age. All my point is, statistics can only point you to look for reasons. It cannot tell you what is necessarily the cause. Maybe not. At least in this case, I don't know what to say further. Yeah. So you have to look into the department wise and then worry about it.
Sir, thank you very much for a very highly illuminating class. I want to ask you one question. That is, the life is as well as good as a life with the probabilities.
Sorry,
Am I
could
correct?
not hear.
Life itself is a life of probabilities. Life.
Life?
Uh,
Oh, okay. Yeah,
Okay.
it's a big problem.
It's a probability,
Yes.
So in this uncertainty world, is it be fair to be a typical person?
What are the other options?
That is what I am asking. Is there any other options?
No, I mean, this is a very broad question, I don't know, but to me, life is always preferable to death, right? Because most of the time we are going to be dead. We get to be alive only a small amount of time. I don't know. I mean, fair, unfair, I don't know how to judge it.
I have a quick question. I was wondering that about the system size. You were saying that let's say for 10,000 it is 1,000, even for let's
Yes.
say like lesser number.
Yes.
Is there a way to choose it? Like how we will let's say for 1 crore I know that there will be.
Right, exactly. Yeah. So that's a very good question. 1,000 here also is 1,000, but what should be the correct answer? So that is given by this. Okay, so let me explain this formula there. So let's say in the actual population there will be some proportion P of people who have opinion X, and other 1 minus P proportion will have opinion different. Let's say we won't do the poll if the P is very close to 0 or 1, then there is nothing to do poll. So P will be somewhere between, maybe 0.5, maybe 0.3, maybe 0.7. Don't worry about it too much. Think of that as P as, let's say, we are trying to find out P, but for this purpose, think of P as 0.5. Then this is telling you the accuracy is, when you put P is 0.5, this becomes half. So it is 1 by 2 square root 10. Okay, so your accuracy is 1 by 2 times square root of the sample size. Even forget the 2, 1 by square root of the sample size. So if you want to estimate that proportion to 1 decimal place, that means you want to estimate it to an accuracy of 0.1. Then you want this 1 by square root 10 to be less than 0.1. That's the accuracy. 1 by square root 10 should be less than 0.1, which means how much? Square root 10 should be more than 10, n should be 100. If you want it to 2 decimal places, you want 1 by square root n should be less than 0.01. That means n should be bigger than 100 square, which is 10,000. So if you want to increase the accuracy, that is how you find the required sample.
Sure, thank you.
What are the guidelines for selecting samples, different type of samples? I hope the question is clear. What are the guidelines for selection of samples? Pardon?
Guideline for?
Selection of samples.
Selection of
samples.
Okay.
You said in Pakistan, you have taken, we have taken 1,000 people.
Yes.
And accordingly, as a probability in India, it should be 7 times. So 700.
No, that
7,
is the point. That is not true.
Yeah. So exactly like that, what are the guidelines for selection of samples?
Okay.
This 1,000 people.
This is one. So this was the answer to the previous question, that I said how to choose the sample size. Sample size is only one aspect. Suppose we decide we have to take a sample of 1,000. How do you find that sample? That is a very difficult question. If I tell you, you pick 1,000 people at random from, let us say, Kerala, for example. How will you go about doing that? It's not very obvious. Okay. So there are various things that are that have to be done. So in principle, you have to somehow make a list of people. Let's say if you had a list of all people in Kerala, let's say it is a very, very long list. Then you have to pick random numbers, 1,000 random numbers from that list, go to those people. That's how in principle it has to be done. In practice, you can't really do that. Now you may say that, okay, so here is one thing I will do. I will just open the telephone page to, let's say, nowadays nobody uses telephone directory, but do people know what a telephone directory is? Okay, there used to be some fat book called telephone directory, let's say. Okay, so let's say you open the page, you can say, let me just randomly open the page somewhere. Let's say I open it to S, okay, and I will take the first 100 people whose name starts with S. Now, 1,000 people, let's say. That could be you might think, okay, how will this, because that's only names of people, it's not going to bias my sample anyway. It could be true, it may not be true, because that may or may not be a good way of doing things, because it's easier, because we don't have the list of all people. So can I take what can be a trap in doing this? What could be a problem? If I choose samples like this, I go to the letter S and I pick the first 1,000 people. Well, for some reason, cultural or otherwise, maybe more women names tend to start with S, men's names don't start with. It's possible, right? I don't know. Maybe there are more common women names. That means that will bias your sample towards having more women than men, or vice versa, something. So even though you may not see an obvious bias in choosing it this way, there may be bias like that. So ultimately what you want is a pure random sample. Pure random sample means all the people in the population, you put a chit there is a box, we have to imagine, where there is one chit for each person in the population. And then you have to mix up that box, pick 1,000 of them at random, those will be your sample. In practice, nobody will do it. No, people will do it in some approximate ways, but then you have to watch out for this kind of biases. Okay, so I don't know if I answered your question, but that is, yeah. There are many others, so that's why I was saying selection bias. Selection bias is something that can happen a lot. If you want to estimate the average size of a family in Palakkad or something, what is the average size of a family? One option is you go to the city center and whoever comes there, you ask them, what is your family size? Okay? And you ask 100 people, you get their family sizes, you average that. Is this a good way to find out family sizes? Average family size. Is this good or not good? Is there any problem with this? So that may be a random sample. You stand in the city center. Well, you should not stand in front of a 5-star hotel and do, because that will bias your population in a certain way. You should not stand in front of a slum or some very poor area. That will bias your population in a different way. But let's say everyone goes to the city center. But is it still then a good way to sample this? There is a fundamental problem in this case. I am just giving you examples. I don't have any general point for you. I am giving you there is a very fundamental problem with this way of sampling. What is it? That is possible, yes. But anything more? Let's say people tend to go to city center anyway. Exactly. So what happens is, if there is a family of size 4 and family of size 2, you are twice more likely to get a person there from a family of size 4. There are 4 people. Whereas from a smaller family, there are fewer people. So this is called size biasing. The very way you are picking the sample tends to be wrong. So in Berkeley, I was hearing some undergraduate students were doing some experiments in biology, and they were having some trouble. The idea was they had to select some rats for some experiment. Their way of selecting rats for the experiment is there is a big box of rats and they put their hand and pick up the rat. Okay. Now, this may not be the best way of picking a random one, because when you put your hand and pick, you will get a bigger one more likely than a smaller one. The biggest, lowest ones are the ones you tend to pick up. So this is all biases. You have to watch out against biases. That's all I can say.
Any further questions?
The case studies you showed today, they show us that our intuition does not work very well.
Yeah.
So how do we actually train ourselves to interpret numbers correctly?
Okay. So, well, yeah, you have to do it, but let me not exaggerate too much also. Of course, I chose examples so that there is something interesting about it. This should not put you off thinking that no numbers can be interpreted or something like that. That's not the case. Yeah, so you have to learn basic statistics and probability to and watch out for biases in the way you are choosing the data or some other thing. Pretty much that's all there is to it. Yeah, so one needs some amount of basic training in statistics, and there are some methods of what are called controlled experiments and various other such things which one has to do. So yeah, I would say you have to learn basic statistics. So if somebody wants to read basic statistics, actually, not a textbook, there are many good textbooks, but there is this series of books called Cartoon Guide to X or Y. I don't know if many of you know these books by Larry Gonick. So there is one book called Cartoon Guide to Statistics. There is also Cartoon Guide to Genetics, Cartoon Guide to Physics, etc. They are very good books, by the way. So there is one Cartoon Guide to Statistics. It's just an easy book to read. I think it's a nice book. One can try to read such things.
If there are no more questions, we would like to thank the speaker for today, Professor Manjunath. Perhaps one of the few lectures that have been extremely interesting and also fun at the same time. And if this hasn't, generated interest in statistics, I don't know what else will. And probably we should also take some pointers from this for our the Math Circle lectures, probably on probability and statistics, to make it more interesting for students and to motivate them further. Thanks a lot, Professor Manjunath. I'll request Professor Sunil to hand over a memento to the speaker.
Good evening, everyone. Thank you all for being here today. On behalf of IIT Palakkad, I would like to extend our heartfelt gratitude to Dr. Manjunath Krishnapur for accepting our invitation to be the speaker for the 4th Pale Blue Dot lecture. Thank you in particular for delivering a talk that was equal parts informative, entertaining, and fun. We would also like to thank our director, Professor P.B. Sunil Kumar, for his encouragement and active support for all of the Institute's outreach and extension activities. Special thanks to the administration of Victoria College for agreeing to provide this wonderful venue for this event today. As you all know, Pale Blue Dot is jointly organized by IIT Palakkad and the Palakkad District Library. On behalf of the Institute, I would also like to sincerely thank Sri Ajayan, Secretary of the District Public Library, Palakkad, for always extending his support to PBD's activities. A big shout out to our CET team for all their technical help this evening. Finally, we would like to express our delight and gratitude to the public of Palakkad for turning up today. We look forward to your continued participation in larger numbers for our future events. If any of you would like to send in your comments or suggestions, you can write to us at blue.@iitpkd.ac.in. And that's all for this evening. Thank you all once again and see you next time.